So we will now proceed with the discussion on the properties of the convolution sum as a mathematical operation. So as a mathematical operation, we would be expecting that the convolution operation or convolution sum operation have would have its own properties, okay, or would exhibit its own properties, which will be usable not only with simplifying yung ilan sa mga operations when you are implementing your convolution sum, katulad nung ginawa natin in the previous example where we used the commutative property of the convolution sum to choose which signal or which sequence must be time folded and shifted, okay, in which we chose the one with the simpler form para mas magiging para yung summation operation natin would be simpler also. Okay, so ayun. So aside from that, the properties of the convolution sum are also useful in simplifying, okay, interconnected LTI systems. Okay, so yung mga LTI systems natin, okay, or yung all systems in general can actually be interconnected. Okay, pwede silang i-connect to each other. Okay, although the connection between these systems will be ruled by some or rather merong the interconnection of systems may have to follow some rules, okay, especially kung sa totoong or sa yung implementation niya talaga o yung realization niya talaga, yung physical realization niya, yung i-interconnect natin. Say for example, kailangan compatible yung mga impedances ng mga systems na to, okay? Or something like dapat ganito yung signal na lalabas, ganito yung type of signal na lalabas sa output ng ating system, okay? And then ito yung tatanggapin ng kabila naman. Okay? So but in this discussion, we will not be considering those rules. Okay? But just remember na this interconnecting systems, whether discrete time or continuous time or any type of systems, okay, will have or will be governed by some rules kapag i-interconnect natin sila. Pero one question is, bakit nga ba tayo nag-i-interconnect ng systems? Okay, why do we interconnect systems? One purpose of interconnecting your system is to actually have a more complex system, okay, or come up with a more complex system. So maaaring yung buong signal processing system natin, or yung buong signal processing system natin might perform many complicated operations on our input sequence. Okay? So, ngayon, for us to prevent the scenario where we will be forced to design that full big complex LTI system, okay, pwede nating i-break down yung mga problems into sub-problems, and each sub-problem will be solved by a subsystem. Okay, so maaari nating i-break down, okay, yung isang malaking system into smaller subsystems in which these subsystems now will be interconnected in some manner para yung magiging equivalent na functionality, okay, o operation na ipe-perform ng mga interconnected systems na to, interconnected subsystems na ito, would be the one or would be equivalent to the operation that will be performed, that the complex system will be performing. Okay? So, paano ba natin ini-interconnect ang mga system? How do we interconnect systems? Okay? So, one way to interconnect systems, okay, is to put them one after another. So, ibig sabihin, yung output niya, no? Ayan. So, we put one system after the other one. So, this interconnection would mean na the output sequence, okay, of the first system here, okay, in this interconnection, yung the output sequence generated by LTI1, okay, will serve as an input sequence to the second system, LTI2. And then LTI2 will then compute an output sequence based dun sa operations that LTI2 system implements. Okay? So essentially, si LTI1 system would have a sequence xn as an input. Okay? Then magkakaroon siya ng output na say x1 o sequence x1n. Okay? And this x1n, okay, this sequence x1n would be or would serve as an input to LTI2 system. Okay, and then the LTI2 system would then compute an output sequence y of n. Okay. Ayun. So, we call this interconnection cascade. Okay? We call this connection cascade connection. Okay? Now, just imagine that LTI1 systems, the subsystem LTI1 and the subsystem LTI2 are represented, okay, using input-output relations. Okay, so instead na si LTI1, okay, this would be represented by an IOR. Okay, IOR1, say, ganun. Okay, and LTI2 or the subsystem LTI2, okay, would be represented by an IOR, okay, 2. Okay, so just imagine that for you to be able to compute the output sequence, kailangan niyo munang i-implement si IOR1 so that you can compute x1n, okay, from xn as an input. Okay, so yun, kung IOR1 yung description ng system 1 natin. Okay, and then we will now use IOR2, okay, and perform the operations indicated in IOR2, okay, with x1n as with the sequence x1n as the input, okay, so that we can compute for the output sequence y of n. Okay, so yung expression, okay, or yung IORs, okay, are not actually very convenient mathematical representations of your systems, especially if you're now dealing with interconnected systems. Okay, okay lang siya kung isang system lang siya, okay, and we're looking for an output given an input, okay lang yun. Okay? Pero kapag ka ganito na, okay, at kapag ka may iba pa tayong set of interconnections na makikita dyan, IORs are very, very inconvenient. Okay? So therefore, this is where impulse responses come into play. Okay? Dito ngayon nagkakaroon ng much use. Okay? Yung impulse response as system representation. Okay? Bakit? Say for example, let's have this system 1, okay? Have an impulse response of H1n, okay? While the second system 2, okay, would have an impulse response of H2n. Okay? Now, when we use use impulse response as system representations, okay, tandaan natin that we are setting these systems to be relaxed. Okay? So, again, tatandaan natin that we will always remember that systems represented by impulse responses are relaxed LTI systems. Okay? Well, anyway, tapos naman na tayo sa consideration that our systems are LTI systems. Kasi nga, again, lahat at this point forward, lahat ng systems na i-consider natin are all LTI systems na. Okay? So, in that case, how do we now simplify, or how do we now compute for y of n here? Okay? So, individually, ganito yung mangyayari. Okay? So, alam natin na for you to be able to compute x1 of n, okay, you need to convolve the input and the impulse response of the first system. So, i-convolve natin si xn, okay, or kukunin natin yung convolution sum, rather, ni input sequence at saka ni impulse response sequence. Okay? So, ayan. Then, after which, since x1 now will serve as an input to the second system whose impulse response is H2n, okay, we will be able to compute the sequence yn, the output sequence yn, by computing for the convolution sum of the input to the second system, which is x1n, and the impulse response of the second system, okay, which is H2n. Yan. Now, obviously, since itong ang convolution sum, just like any other operators that we have, pwede natin itong say function na to, or yung equivalent ng mga functions na to, okay, or ng function na to, or the equivalent expression of this function or this sequence can actually replace this sequence here in this expression. Okay? So therefore, it is possible na makompute pala natin si y of n by having the convolution sum first of x of n and h1 of n. Okay? Then, i-convolve natin ngayon itong convolution sum nila, i-convolve natin, or kukunin natin yung convolution sum, okay, nung convolution sum na to and h2n. Okay? So, i-convolve natin ito with h2n. Okay? So, lagyan natin ng color scheme para ano. So, ayan, no? Okay. So, this is how interconnected systems, okay, or how this interconnected system would actually compute for the output. And in this case, hindi na natin we really don't need this intermediate signal na to. Okay? Because y of n now, the output sequence is now expressed in terms of the arbitrary input and the impulse responses. Okay? So, ayan. Now, one property of your convolution sum operation, okay, is that it is associative over the convolution sum. Okay? So, ang associative or associative property, okay, ng mga operation means you can associate operations depending on in any order. Okay, yung association ng operations at saka ng operands can be done in any order. Okay? So, say for example, associative ang plus. Okay? Because adding 4 plus 3 first, and then the sum of this when added to 7, okay, will produce the same result if we add 3 plus 7 first. Okay? And then add that sum with 4. Okay? So yung association, okay, or yung grouping essentially, okay, ng mga operations doesn't matter. Okay? So you can do the association of operations kahit saang order. Okay? So ganun sa convolution operation. Okay? So it is possible that yung operation might be associated with the first two operands. Okay? With the third operand to be operated upon after mong makuha yung results nung first operation. Okay? And since the convolution sum operation is associative, okay, you can instead operate first on the last two operands. Okay? Pwede nating unahin yung or pwede nating i-operate yung last two operands, okay? By convolution sum, and then so ito 'yun. Okay, and then yung result nung convolution sum nila, okay, nung last two operands will be operated or will be convolved with the first operand. Okay? So, ayun. Yun yung associative property ng convolution operation. Okay? So, which means dito, pwede ko palang pagpalitin yung association, okay, nung operation ng convolution sum. So, instead of actually associating or performing the operation on the first two operands first, I can again, okay, using the association property, okay, of the convolution sum operation, okay, I can find the convolution sum of the last two operands first, okay, with the result, okay, to be convolved with the first operand. Okay? So, dito, wait lang. Okay, so, inalo lang natin yung original form nung expression para makumpara natin. Okay. So, what happens then now? Okay, so again ito, we use the associative property of the convolution sum, convolution operation. Okay? So ngayon, the change of association of the operation actually would imply na pwede ko palang i-reduce itong dalawang system na to. Okay? Into an equivalent system. Okay? Whose impulse response is this. Okay? Kasi, tingnan niyo mabuti. These two, okay? Itong dalawang operands na to, okay, are both impulse responses. Okay, so therefore, these two operands are associated with a system. Okay, so dito operands, okay, are associated with systems. Okay, but since this operation would produce a simpler a simpler expression, okay, or an equivalent expression. Say for example, that equivalent expression is say h of n. Okay? Kaya that equivalent expression is h of n. Okay? So, ibig sabihin, physically, ito palang cascade connection ng dalawang LTI system natin, okay, can actually be represented by a simpler system, okay, by a simpler and equivalent system, okay, so yung equivalent system natin ngayon, okay, ay doon natin sa para makita natin siya, okay, so ito ngayon, iyan natin, mare-reduce natin siya into an so ayun, mare-reduce natin makakapagsulat tayo ng equivalent and ng equivalent system, okay, dito sa original system natin. So this is the we consider this to be the original system. Okay? And this to be the equivalent. Okay? Equivalent system. Okay? And pag sinabi niyong equivalent system, okay, or equivalent system to the original, okay, ibig sabihin nun, both systems, okay, both the original and its equivalent system would implement the same rules on the input sequences, okay, and would produce the same the same output sequences, okay, for that given input sequence, or for an arbitrary input sequence. Okay, so which means kung ang original system natin takes in x of n, okay, as an input, it will still produce the output sequence phi of n, okay, even though it is now a system, okay, that consists only of one or single block, or a single system na lang siya, okay, and that that system is now represented by an impulse response h of n. But again, remember that this h of n is equal to the convolution sum of h1 of n, okay, and h2 of n. Okay? So, ganun pa rin 'yun. So, ano yung idea dito? If you have a complex, big interconnected systems, or interconnected systems, it is possible that we can write, okay, a much reduced equivalent system to that complex, big system, and make those two systems equal. Okay, so possible, okay, it is possible to produce a complex multi-pole interconnected LTI systems into simpler equivalent systems. Ayun. So, yun yung idea dito. Okay? So, the idea is that this complex multiple interconnected LTI systems is equivalent to that simple system or reduced system. Okay? So, yun yung idea. Okay? And how were we able to do that here? Okay? In this case, in the case of cascaded systems, okay? In case of cascaded systems, ginamit natin yung associative property of the convolution sum operation. Okay? So, that's one. Okay? Now, it is also possible to implement yung commutative property ng convolution sum dito. Okay? So, aside from allowing us to change the order of operands for a convolution sum operation. Okay? The commutative property would also allow you to rearrange, okay, systems that are connected in cascade. So kung meron kang system that are connected in cascade, okay, so ito yung H1 natin, tapos ito yung H2. Okay, ito yung system 1 natin represented by H1. Ito yung system natin represented by H2. Okay, so by commutative property of the convolution sum, okay, kasi itong H1 tsaka H2, alam natin, pwede natin gawin H1 of n convolve with H2 of n. Okay? And by commutative property, pwede pagpalitin yung order ng operands. Okay? So you have H2 of n convolve with H1 of n. Sa system implementation, ang implication nun is that it is possible for you to actually rearrange those system. Okay? So without altering itong signal na to. Okay? Without any alterations or any changes dun sa signal na to. Okay? The systems, okay? The order of the systems or the systems may actually be rearranged. Okay? So sa cascade connection lang ito ha. So sa cascade connection, okay, or for systems connected in cascade connection, okay, the commutative property of the convolution sum allows you to rearrange, okay, the order of the system or rearrange the systems themselves. Okay? So ayun. Actually, dun sa sinasabi ko kanina that this signal will be unaffected by that rearrangement of the two systems. Happens only under the assumption that H1 does not load H2. Ibig sabihin yung impedance, okay? If these are individual circuits, okay, say these are individual circuits, meron kasing output impedance itong si system H1, okay, at merong input impedance itong si H2, okay. Now, pagka magkaiba kasi yung impedances na yun, yung output impedance nito at saka yung input impedance nito, pag pinag-interconnect nyo siya or kapag kinonnect nyo siya as as the output of this to the input of this, magkakaroon ng loading effect, okay, which means that the circuit H1, okay, or system H1 would actually cause or would actually look to H2 as a load. Okay? Tapos ganun din si H2. Ang tingin naman niya ni H2 kay H1, ano naman source. Okay? So ngayon, the greater the mismatch between the impedances, okay? The worse the loading effect. Ang nangyayari with the loading effect is yung power na supposedly ita-transfer ni H1 papunta kay H2 via this signal, okay, is actually nababawasan. Okay, bumababa siya. Okay? So, yun, ganun mangyayari. Kaya ang mangyayari ngayon actually, kung may loading effect, kung ano yung ipoproduce na sequence ni X1N, okay, i-adjust pa natin si X1N with a certain factor, okay, to account for the loading effect. Okay, tapos, iba ngayon yung magiging input signal ngayon input sequence ngayon kay H2N. So, that would be, say, X11 na. So, modified na siya. Okay? So, that is loading effect. Okay? Pero, para hindi tayo masyadong mahirapan, okay, sa ganitong mga scenario, we will always assume, okay, we will take out yung discussion ng loading effect in this interconnections. Okay, so wala kumbaga parang hindi mo natin concern yung loading effect na yun. Okay. So kapag walang loading effect kasi, so yeah, buong-buo yung power na ita-transfer ni H1 papunta kay H2. And that power will be in the form of the sequence X1N. Okay. Either power or energy, depende kung anong signal si X1N. Okay. So ganun yan. Okay. So ngayon, the problem kasi kapag consider balikan natin yung loading effect. The problem kasi with us considering the loading effect, hindi natin magagawa basta-basta itong itong rearrangement na to. Okay, when loading effect is considered. Okay, dahil mababago kasi itong signal na to. Okay, this signal would be modified. Okay, bakit? Kasi maaaring say for example, kung may loading effect, okay, let's say na ang output ni H1N to XN is X1N, okay, and then due to loading effect, say i-scale natin si X1 by A to produce X2N or X11N, which this now would be the input to H2N. Okay? Pag pinagpalit natin kasi sila, okay, at merong loading effect, at merong loading effect, okay, which means that the output impedance of H2 is different from the input impedance of H1. Okay? So ngayon, kapag si H2 nag-compute ng output with Xn, okay, and say it produces a signal X2N, okay, yung scaling factor dito, which is say for example B, would have a different value than the scaling factor na ginamit natin dito. Kasi nga, iba na yung magiging loading effect naman. Dahil magkaibang input-output impedance mismatch yung tinitingnan natin. Okay, so therefore, it would be really hard for us to consider loading effect in this scenario. Okay, so that is why, yun nga, sa mga ganitong for us to be able to simplify everything, di natin titingnan muna yung loading effect na yun. Okay, so there. So again, the commutative property of your convolution sum allows for rearranging of systems connected in cascade. Okay, so if the associative property can reduce, okay, or can reduce multiple cascaded system into a single system. Okay, suot natin yan. The associative property of convolution sum, okay, allows the reduction of multiple cascaded systems into a single equivalent system. Okay? So, yan. So, the associative property of the convolution sum allows the reduction of multiple cascaded systems into a single equivalent system. And here, emphasize natin yung ginamit nating term na multiple. It means that this rule will also work for 3 or more cascaded systems. Okay? Kahit ilang cascaded systems ang naka-connect dyan. Okay? The associative property of the convolution sum would allow you to reduce all of those cascaded systems, okay, into single equivalent system. Okay, so it means that 2 or more. Okay. Now, so this associative property, no? While the commutative property of the convolution sum, okay, allows for rearrangements of systems connected in cascade. So kung meron kang 2 or more systems that are cascaded, okay, pwede nating i-rearrange yung mga systems na yun, okay, using the commutative property of the convolution sum. Okay? Okay. So now we proceed. Okay. We proceed now with in working on example 4, which asks us to determine the impulse response of 2 cascaded LTI system, or for the cascade interconnection of 2 LTI systems having impulse responses of H1 tsaka H2. Okay? So, kung i-visualize natin yung problem in example 4. So again, meron tayong dalawang system, okay, that are connected, okay, in cascade. So yung so the input to the first system, okay, produces the output of the first system, which serves as an input to the second system, and that now is used by the second system to produce the output of the 2 interconnected systems. Okay. Now, say the input to this system is x of n, okay, and the output to the to this entire thing is y of n, okay. And then we have the first system represented by h1 of n, and the second system represented by h2 of n. So what we have learned from the previous discussion, okay, or applying what we have learned from the previous discussion, we can use the associative property of your convolution operation, okay, so that this two cascaded system can be reduced, okay, into an equivalent system. So i-reduce or i-rewrite natin tong system na to into an equivalent and reduced system. So that is magiging isang system na lang siya. With again, the input to this system is x of n. Okay, and the output to this system is y of n. So, pagka perform pala tayo ng reduction, isa sa mga one thing that we always have to look for is the preservation of the input and the output signals. Okay? Kailangan ang rule ng reduction ng interconnection system, or ang rule ng rewriting, okay, or rewriting your system into an equivalent system is that dapat yung input at saka yung output signals natin, okay, will be preserved. Okay? So, sulat natin to. Yung point na yun. When rewriting systems into equivalent forms. Equivalent forms. Okay. The input and output sequences must be preserved. Okay. And actually, hindi lang yan. Okay. May mga ilang signals pa. Okay. That during the process of rewriting your systems, may mga signals tayong makikita na dapat ma-preserve din siya. Otherwise kasi pag di siya na-preserve, okay, or pag hindi na-preserve yung presence ng signal na yun, okay, magbabago yung system natin, okay, and therefore hindi na siya equivalent na system. Okay, so always see to it that whenever you are rewriting systems, okay, into equivalent forms, may mga yung rule of preserving the input and the output sequences must be always observed. Okay, and later on kapag nagkaroon tayo ng pagkakataon to be exposed to an example where we have to preserve also other signals besides the input and the output signals or the output sequences. Okay, so ayun, yun yung point natin dito. Okay, so ayun, here na-preserve natin yung input at saka yung output, kung paano sila pumasok dun sa original system natin. Okay, kung paano pumasok si signal x of n sa original system natin. Okay, ganoon din siya mapifeed dun sa equivalent system natin. Okay, so ayun. And of course, the output sequence produced by both the original and the reduced system ay are still the same. Okay. So here, we have already, if we are to use associative property to be able to rewrite this system into an equivalent system, we will know for that, or we will know that that equivalent representation h of n, okay, is actually determined as the convolution sum of h1 of n and h2 of n. Okay, so ibig sabihin, itong dalawang to, kukunin natin yung convolution sum nila. Okay. So, ayun, no? So, here, again, sinasabi nga niya dito, if two systems represented by impulse responses h1 and h2, okay, are connected in cascade, okay, then the associativity of the convolution sum algorithm implies that the two systems can be reduced into an equivalent single system, okay, whose impulse response is the convolution sum of the individual impulse responses of the original system. Okay? So, now, medyo kasi sanay tayo sa formula ng convolution sum na na yung long form ng formula ng convolution sum as y of n equals summation of x of k, okay, h of n minus k for k equals negative infinity up to positive infinity. Okay, so medyo i-modify lang natin ito ng konti. Okay, so that is, instead na x, let's have this to be h1. Okay, while ito, gawin natin h2. Okay, and then itong y, instead na y, gawin natin h. Okay, which now represents the equivalent impulse response. Okay, that represents the two cascaded system, or the two cascaded systems. Okay, now if we have or if we substitute yung h1 of n as ano yung h1 of n, 1 hat raised to n u of n, and h2 of n to be 1/4 raised to n u of n. Okay, so wala naman tayong reason na pagpalitin yung operands natin, no, when we perform the substitution. Okay, wala tayong motivation kasi pareho lang naman yung form niya. Pareho naman exponential multiplied to step sequence yung dalawang sequences natin. So therefore, whether ito yung i-fold shift natin or ito, pareho lang. Okay, so we will substitute these sequences dun sa algorithm natin, which leads us to this expression. Okay, so again, once na ginawa niyo yung substitution, magpapalit na rin kayo ng variables. Okay, so yung for 1 raised to n u of n niyo, yung n magiging k, tapos yung n ng u of n nyo, okay, magiging u of k. Okay, so ito yun. While h2, once na sinubstitute natin, yung n dito magiging n minus k. So this becomes 1/4 of n minus k. Okay, while itong u of n natin dito becomes now u of n minus k. Okay, so applying yung natutunan natin from example 3 with regards dun sa values nitong dalawang sequences na to and the limits of your summation operation. Okay, again, we recall na ang magiging value nito is 1. Okay, or idiretso natin. Let us simply change the limits. Okay, to k equals 0. Okay, because of this signal. Okay, which puts or which causes the entire product sequence to become 0 when k is negative. Okay, while this sequence naman causes the upper limit of your summation sign to reduce to n. Okay, So, magiging n na yung upper limit natin. Again, because this sequence, okay, is 0 for um, for uh, for your k greater than n. Okay? So, in this in this interval of k, sa interval na 0 to n para sa k ninyo. So, when k is between 0 and n, okay? Itong dalawang to, this sequence and this sequence are both 1. Okay? So, therefore, mare-reduce natin ngayon yung ating expression na to into this. Okay, into this expression. Okay. Now, using loss of exponents, we can rewrite this this factor as 1/4 raised to n and 1/4 raised to negative k. Okay. Now, since ang index ng summation niyo is k, okay? Yung mga isa-sum up niyo, itong factor na to will become a constant. Okay? Dun sa sa bawat term ng sum niyo. Okay? So, kasi n kasi yung exponent niya. While the index of your summation is k. So, ibig sabihin, pag in-expand natin itong summation na to. Okay, itong summation operation na to. This factor, okay? This particular factor here, okay? Will be simply present in every term of the summation operation. Okay? So therefore, pwede natin siyang i-factor out from there. Okay? Magiging common factor kasi siya sa lahat ng terms pag in-expand natin yung summation operation. So therefore, i-add natin siya, ipa-factor out natin siya. So magiging ganito. Okay? Now, since this is 1/2 raised to k and this is 1/4 raised to negative k, let's write this to be ito 2 raised to 2k instead. So since negative yung exponent nito, ire-reciprocal ko siya. So magiging 4 raised to k ito. Okay, so magiging 4 raised to k muna siya. Okay, and then yung 4, okay, just to make the base of this term or this factor similar dun sa base nung isa pang factor natin, which is this one. Okay. I'll rewrite yung 4 raised to k na 2 raised to 2k. Okay, kasi 4 is 2 raised to 2 eh. So therefore, 4 raised to k is 2 raised to 2k. Okay, while 1/2 raised to k, pag ni-reciprocal natin yan, magne-negative yung exponent niya. So yung 1/2 raised to k natin becomes 2 raised to negative k. Now, this product, okay, simplifies to 2 raised to negative k plus 2k using loss of exponents. Okay, or 2 raised to k. Okay, so yung product na to becomes this factor. Okay, or becomes this reduced factor. Okay. So therefore, magiging ganito ngayon yung expression natin. Okay, so from here, mare-write natin ngayon yung expression natin into this. Okay, so again recall na nilabas natin yung factor na 1/4 raised to n dun sa or from the summation operation, since nga siya, lumalabas na siya ay common term or common factor to all terms of the summation operation. Okay, while the product sequence or the remaining product inside the summation operation is rewritten into the reduced 2 raised to k. Okay? So now, pag in-expand natin ngayon yung itong summation operation natin. Okay? So we see na makakabuo tayo ng geometric series. Okay? So this summation, okay, is actually a finite geometric series. Okay? With the upper or with n plus 1 terms. Okay? So this is a finite geometric series with n plus 1 terms, and yung base ng natin ng geometric series natin, or essentially yung common ratio ng geometric series natin is which is identified as A, is equal to 2. Okay? So this is this summation, okay, is actually a finite geometric series with n plus 1 terms and the common ratio, okay, equal to 2. Okay? So now we recall that the sum, okay, of this finite geometric series having n plus 1 terms and common ratio of 2, okay, to be this expression. Okay? So again, galing yan sa previous topic natin. Okay? So in this case, the previous equation now will be rewritten, okay, or can be rewritten now as so ito pa rin yung factor na 1/4 raised to n. And then yung factor na to, which represents the sum, okay, of the finite geometric series. Okay? So takbo natin yan from here. Okay? Which when we rewrite the expression on the right side, okay, on this side, okay, will lead us to this reduced equivalent expression. Okay, so wala naman tayo siguro ma-simplify pa dyan. Okay, so just simply h of n is now 1/4 raised to n multiplied to 2 raised to n plus 1, okay, minus 1. Okay, by the way pala, may I remind everybody that kapag nagsasolve tayo ng mga sequences or in any way, okay, I would like you to practice to practice consistency, okay, in writing your analytic solutions. Okay, consistency in terms of what? Okay, in this case, yung consistency that consistency is reflected on preserving yung fractional form nung H1 tsaka ng H2 natin. Okay, since the H1 and H2 are exponential sequences with the base of the exponential written as fractions. Okay. Observe na sa lahat ng parts ng analytic solution natin, hindi natin binitawan yung form ng yung fractional form na yun. Okay? So hindi natin siya binitawan. So you will not be able to see at any point in the analytic solution that we have used, say, 0.5 raised to n u of n and 0.25 raised to n u of n, okay, as equivalent for H1 and H2n. Okay, H1n and H2n. Okay, so kaya hindi ko na-express yung final expression ko as a fraction. Okay, so yun yung request ko. Okay, whenever you are dealing with problems that require you to write an analytic solution, tapos yung mga given ninyo is written in a certain manner, okay, I would like you to adhere, okay, and maintain the form, okay, of the given. Okay, kung naka-fraction yung given niyo, okay, kung fractional yung given niyo, dapat ang analytic solution nyo naka-fractional form din. At yung sagot nyo, yung final na answer nyo, dapat naka-fractional form din or naka-rational form din. While kung naka-decimal naman siya, okay, say for example, if this is h1 of n, kung ang given is instead h1 of n equals 0.5 raised to n u of n, okay, and say h2 of n equals 0.25 raised to n u of n, para ma-apply nyo yung rule na sinasabi ko, dapat pagka, say for example, pagka kinumpit ko yung h of n ng summation of h1 of k, okay, times h2 of n minus k, for k equals negative infinity up to positive infinity. Pag in-apply ko yung rule na sinasabi ko sa inyo, okay, that is yung consistency ng ng form of the given, okay. I would have the substitution, okay, look like, or have write the equivalent expression after substitution to be summation of 0.5 raised to k times 0.25 raised to n minus k multiplied to u of k multiplied to u of n minus k for k equals negative infinity up to positive infinity. Okay? And then, tuloy-tuloy natin yung solution na yan. Okay? The final answer will be expressed as 0.25 raised to n. Okay? Multiplied to 2 raised to n plus 1 minus 1. Ganun yung pwede kong isulat as the final answer. Okay? So, again, since yung binigay sa akin dito, sa problem na to, is naka-decimal form yung mga yung mga bases ng exponential sequences ko, then I would have the final expression also be expressed in decimal as decimal numbers. Pero kung fractional yung given, sana i-preserve natin yung fractional form yung natin. Ang target kasi natin is makita natin yung mga values that are in the given dun sa final expression natin. Okay. So, actually, in fact, I can instead of actually writing h of n in this form, I can actually rewrite yung this h of n as 1/4 raised to n multiplied to 1/2 raised to negative n minus 1. Okay. Then minus 1. Okay. So, pwede ko siyang i-write ng ganyan. Now, ano yung gusto kong palabasin dito? Yun nga, para makita ko pa rin yung 1/4 at saka yung 1/2, which are the bases. Okay? Yung bases nung nung impulse responses, okay? Nung original systems ko. Okay? But this is okay now. Okay na to. Anyway, 2 is a rational number naman, so okay lang yan. Okay? But this is also okay. Okay, so pareho lang yung dalawang expressions na yan. So now that we have the expression, okay, of your h of n, for your h of n, or the equivalent expression for your h of n, okay, it would now mean that our reduced system, okay, would now have an impulse response sequence, okay, that is the terms of the expression or the values computed from the expression 1/4 raised to n multiplied to 2 raised to n plus 1 minus 1. So yun na our reduced system now would have an impulse response, okay, whose terms of the impulse response sequence, okay, would be computed, or would be the set generated by this expression, okay, for n greater than or equal to 0. So ibig sabihin, yung impulse response natin para sa equivalent reduced system natin, okay, that represents the original interconnected systems, okay, cascaded systems, would have an impulse response na ang terms ng impulse response, or the values of the sequence of the impulse response can be computed, okay, using this formula. Okay, so ang gagawin natin dito sa next steps ng problem is not really not really part of of the problem, but we would like to actually check, okay, or verify yung nakuha natin. Okay? And we would also like to see how MATLAB can actually be used in this case. Okay? So, ang gagawin natin is we will try to feed this or we will try to feed the original interconnected systems with an arbitrary signal xn, and then try to compute for the output yn. Okay? For the output yn. Okay? And then feed this feed the equivalent system, okay, with feed the equivalent system with the arbitrary signal that we have used in the first case, okay, and try to compute the output of the equivalent system. Kapag yung sequence na to nung the sequence produced by the original system and the equivalent system are equal, okay, or are equal sequences, okay, we can conclude na yung dalawang systems natin are equivalent processes, okay, and are therefore equivalent systems. Okay, so ayun, here ang gagawin natin in both cases, we will be using numerical convolution, okay, using the function fcon m. Okay, again, if you can remember, this fcon b is fcon b function is a user defined function, okay, which is provided to you, okay, already. So here, the arbitrary signal that I used in this endeavor is simply a unit step signal. So yung xn na ginamit dito is simply u of n. Okay? And this xn, okay, is actually defined, okay, within the interval -5 to 20. Ayun, yun. Okay. Now, the sequence H1n, okay, the impulse response, the terms of the sequence H1n is or can be computed using the expression 0.5 raised to n or 1/2 raised to n. Okay? Since hindi ko pwede ko namang isulat as 1/2 or 0.5 sa MATLAB. Okay? So 0.5 raised to n, okay? Multiplied to u of n. Okay? So yung by substituting or by replacing yung n natin dito with values, okay, from -5 up to 20, we will be able to compute the sequence or the impulse response sequence for the first system. Okay? So, yun. Mapupunta siya ngayon dun sa array H1. Okay? Now, here we have assumed that the output of the first system to xn is assigned to be L. Okay? YL1. Okay? YL1. Okay? And would be defined, okay, in the interval or would be defined in the interval that is actually similar dapat dun sa original interval natin. Okay? So dapat ang interval nitong YL1 natin will be defined within -5 to 20. Okay? The thing is that since we will be using numerical convolution, and that yung ating impulse response that is supposedly of infinite duration was truncated to become a sequence of finite duration. Okay? So therefore, magiging inaccurate yung natin, magiging inaccurate yung results ng numerical convolution sum algorithm natin. If we go beyond n, if we go beyond 20, okay, or we go beyond the terms of the sequence YL1, okay, for n greater than 20. Okay? So, therefore, natin, yung terms nung or yung interval in which yung YL1 natin is to be defined is ipapareho natin dun sa original interval natin. Okay? So, which means that we will have to truncate the convolution sum. Okay? We will have to truncate the sequence, okay, produced by the numerical convolution sum, okay, into a sequence that is defined for n between -5 hanggang 20. Okay, so again, napag-usapan natin to last time that that numerical convolution sum will produce erroneous results. Okay, kapag yung terms nung nung sequence natin is different from the original. Okay, while while the problem, okay, states that h1n is 1/2 raised to n u of n times u of n, implies that h1 is of infinite duration. Okay, nung inilagay natin siya sa loob ng MATLAB, okay, we have to truncate, okay, we have to truncate h1 to, or you have to truncate the sequence h1 to become a finite duration sequence. Okay? So ngayon, ang implication yun is that yung value or yung sample value of h1, okay? The implication is that the sample value h1 at n equals 21, okay, is not equal to, okay, i-green natin to kasi yung green represents the original sequence. Yan. Okay, so yung sample value, okay, of h1 at n equals 21 and beyond actually, okay, and beyond, okay, h1 up to infinity, okay, is not now equal or will not be equal now to the values of the sequence of the truncated h1 from 21 up to h1 of up to h1 to infinity. Okay, since this truncated h1 is now a finite duration sequence, lumalabas ito kasi na siya, lahat yan 0 na. Okay, sa original sequence nyo, hindi kasi ito 0. These are non-zero values supposedly. Okay, so yun yung difference ng dalawa. So therefore, since dito magsisimulang mag-iba, okay, diyan magsisimulang mag-iba yung value nung truncated sequence niyo, okay, at saka nung original sequence niyo sa n equals 21 and beyond. Okay, so if we actually produce, okay, the convolution sum of xn, okay, or the sequence x, okay, nl, and truncated h1, okay, the truncated sequence h1 using numerical convolution, okay. While this would result to to a sequence, okay, a sequence YL1, okay, whose length, okay, whose length would be meron tayong na-define natin kung na-discuss natin before kung paano alamin yung lengths or alinin yung length ng ng resulting sequence of the convolution sum for finite duration sequences, no? So, review natin siya. So, we recall that the length of the resulting sequence, okay, of the numerical convolution sum of two sequences, two finite duration sequences, x at saka h1, okay, is the length of your sequence x plus the length of your sequence h1, okay, and then minus 1, okay. So since both your sequences x and h1 have lengths of 26, okay, both of them are length 26 sequence, okay. Your y1, okay, the length of your y1 would be this is 52 minus 1, so this is 51. So meaning there are 51 terms, okay, or there are 51 sample values in your sequence y1, yl1, okay, and that your yl1, okay, would be defined now, okay, for n between yung lower limit nito, again, if you can recall, is the sum of the lower limits of the intervals for your sequence x at saka sequence h1. So since both of them are defined starting from n equals -5, so meaning yung sequence or yung sequence resulting from their convolution sum would be defined, okay, or the first term or the first sample value, okay, of the sequence, okay, resulting from the convolution sum of sequences x and h1 would be -5 plus -5, okay. So yung lower limits nung dalawang intervals nung input sequences natin, okay. So which means yung lower limit ngayon nung YL1 natin must be -10, okay, and its upper limit is again yung sum nung upper limits nung interval for your x at saka h1, okay. And since both of them are defined or the last sample values are defined for n equals 20, both of those sequences, okay, so lalabas ngayon na yung upper limit, okay, nung nung interval ninyo for the sequence YL1 is actually 40, okay. So kaya pag tinignan niyo yung length nito or kung gaano karami yung terms ito, okay, this n would have actually 40 minus -10 plus 1 kasi including yung n equals 0. So that gives you 51 terms, okay, or 51 values for your time index vector, which also results to 51 terms of your sequence YL1. But again, ito nga yung sinasabi natin, okay, mag-iiba yung value, okay, nung original sequence niyo at saka nung truncated sequence niyo that was used in MATLAB to compute for the numerical convolution, numerical convolution sum, okay. So therefore we will limit, okay, we will limit the the interval, okay, in which your YL1 would be defined dun sa dun sa uh, 20, okay, as the upper limit. Okay, kasi pagdating ng n greater than or equal to 21, iba na yung value ng convolution sum. Okay, so that's one thing. Okay, in the same manner, yung lower limit ng YL1 natin must be negative 5. Okay, again, because of the truncation process na ginamit natin so that we can input this into MATLAB. Okay, yung values supposedly ng H1 of negative 6, okay, sa original sequence, okay, green pala gamitin natin so that we know that is the original sequence. Okay, so sa original sequence, okay, yung sample value of H1 at n equals negative 6 and beyond, okay, up to the sample value of H1 when n is infinity, of negative infinity. Okay, so from H1 negative infinity hanggang H1 of negative 6, okay, of your original infinite duration sequence, hindi yan equal dun sa values, okay, of your truncated sequence. Okay, that is yung value ng or yung sample value ng H1 of negative 6 from H1 of negative infinity hanggang H1 of negative 6 are not equal dun sa original infinite duration sequence natin. Okay, so therefore, kapag in-implement natin yung numerical convolution sum algorithm using the truncated sequence, okay, dito magsisimulang maging erroneous yung value nung sequence niyo. Okay, o nung convolution sum sequence niyo. That is for n equal to negative 6. Okay, n less than that. Kasi up to negative infinity. Okay, so for n less than n equal to negative 6, yung value ng y of L1 ninyo, okay, would now be considered to be erroneous. And that error is caused by the truncation of H1, okay, to be a finite duration sequence, okay, instead of being an infinite duration sequence. Okay, so same thing, no? For n greater than or equal to 21, and for n greater than or equal to 21, yung values ng sequence YL1 nyo is also erroneous. For the same reason. For the same reason. Erroneous. Okay. For the same reason. Okay. So, dahil sa truncation na ginawa natin, so that we can input the H1 sequence, okay, into your MATLAB. So, ayan. Now, YL1 now, okay, the sequence YL1 now, okay, now that we are able to compute the sequence YL1, okay, and we are also able to define yung interval kung saan siya nakadefine dapat, okay, which is still negative 5 to 20, okay, YL1 now becomes an input to LTI system 2, okay, which is now represented by the sequence, okay, or the impulse response 1/4 raised to n u of n. Okay, but again, this being an infinite duration sequence, okay, para ma-implement natin siya sa MATLAB, kailangan ulit natin siyang i-truncate. Okay, so ita-truncate natin ulit siya as h2 n equals 1/4 raised to n, okay, 1/4 raised to n u of n, Okay? For n, between -5 to 20. So ngayon, ito is now a finite duration sequence. So ito na yun. Yan. That command generates the sequence of this impulse response. Okay? Pero again, truncated version ito nung original infinite duration sequence natin. Okay? So we now perform the numerical convolution sum and compute for YL2. Okay, the output of the second system to YL1. So we first represent the output of H2 to YL1 to sequence YL1 as YL2. Okay? And again, the sequence or the resulting sequence of the convolution sum, okay, will be correctly defined within the interval, again, -5 to 20. Okay? Since both your input, okay, YL1, and your truncated impulse response, okay, are defined also in the same interval or within the same interval. Okay? So, in that case, YL2 now, okay, is now the output of the system, okay, or the sequence that represents the output of the two systems to a unit step sequence input. Okay, so lumabas, meron tayong system, nag-input tayo ng U of n. Si first system nag-produce ng sequence and it served as an input to the second sequence, second system, which produce y of n as your output. Okay, so this y of n is represented by the vector yl in this command. This is now yl. Okay, and again yl would be, or the values of or the sample values of yl is correct for within the interval of -5 to 20. Kaya yun lang yung kinuha natin. From -5 to 20 lang yung kinuha natin. Okay. So, this is now the values of your sequence y of n, which represents the output of the two cascaded system. Okay. Now, the equivalent system, okay, again, is represented by the impulse response h of n. Okay, which is or which can be considered as a sequence, okay, whose values are in the set of again, yung na-compute nating expression, 1/4 raised to n multiplied to 2 raised to n plus 1 minus 1. Okay, when n, when n is between -5 or within -5 to +20. So yung elements of this set, okay, represents your h of n. Again, truncated. Okay, this is the truncated h of n. Okay, as opposed to the original h of n of 1/4 raised to n multiplied to 2 raised to n plus 1 minus 1. Okay, in which your h of n will be computed for n greater than or equal to 0. Now, this h of n, again, originally is an infinite duration sequence. The number of terms of this sequence is infinite. Okay? But then again, para magamit natin siya sa loob ng MATLAB, itatrancate ulit natin siya. Okay? That is by limiting the interval of your n. Okay? And then computing for the sequence or the sample values of hn. Okay? And then, yung sample values ng hn, okay, generated from this set, okay, will be convolved with the sequence xn, which is yun nga, step sequence siya. Okay? Also, defined within the interval -5 to 20. In fact, pati itong x of n ninyo is also is being truncated. Okay? By defining it within the interval -5 to 20, you also truncate your step signal. Okay? In which we should have the idea that step sequences are infinite duration sequences. Okay? So, here, nagpalit lang tayo ng designation ng n. So, instead of NL, we now use NR para sabihin nyo magkaiba siya. Okay? So, still, pero pareho lang naman yung elements nun. Still, -5 to 20 pa rin siya. Okay? This generates the arbitrary input signal, which is again a step signal or step sequence, okay, from -5 to from -5 to to +20. Okay. So your interval is from -5 to 20. Okay. And then this sequence H, okay, is generated using yung na-compute nating or na-determine nating expression, which is ito nga. Okay. So with that, okay, now that we have the sequences for X, the arbitrary input, and H, the equivalent impulse response sequence, okay, although truncated to pareho, okay, we now compute for the output sequence by numerical convolution sum. Okay. Taking note that because of the truncation that we did, okay, yung YR ninyo, yung sequence YR ninyo, would have correct values or would have correct sample values for or within the interval -5 to 20 only. Okay? So, meaning, mapagpapareho natin si YR, which is generated using the equivalent system, and si YL, okay, which is generated using the cascaded system, okay, within this interval lang. Okay? So, yun ang i-compare natin. So, this is the sequence generated using the two cascaded systems. Okay? So, by convolving xn with h1, okay, and then yung resulting sequence na to would serve as an input to h2. So, to compute the output of that is will require the operation convolution sum also, okay, to have us arrive at the overall or the total output sequence, okay, of the two cascaded systems. Okay, and this one, okay, is generated, okay, using the equivalent reduced system. Okay, so that is the use of h of n, okay, instead of the two individual impulse responses. So, pansinin natin na within the interval -5, okay, within the interval of n -5 up to 20, okay, so ito, check natin yan. That's -5 to 7. Ito naman, 8 to 20. Okay, we see that the sample values in each individual time instance, okay, or indices, okay, are similar or are the same. Okay, so therefore, we say or we conclude that these two, okay, since both of these systems, okay, produce similar sequences, similar output sequences to the same arbitrary input sequence, okay, we say that these two processes, okay, so yung process of computing the output from the two cascaded system, and then yung process of computing the output, okay, using the equivalent reduced system, okay, we say that these two processes, okay, are equal processes because we were able to show na parehong output sequences ang mapoproduce niya for the same input sequence. Okay? And that verifies yung ano natin, yung nakuha nating expression for your equivalent h of n. So yung nakuha nating h of n dun sa ating reduction is or we conclude that this is correct. Okay? So there. That's how we use MATLAB to verify your answers. Even if your problem is analytic, pwede nyong gamitan ng numerical proof. Okay? So that you will be able to increase yung confidence niyo with your answers. Okay? Now, another property, okay, of your convolution sum is that it is distributive, okay, over addition. Okay? So, so pag sinabi nyo an operation is distributive over addition, okay, it means that yung operation niyo would have one of its operands as a sum, okay, of two functions or two sequences. Okay? So ibig sabihin, say operation, may operation ka. So say this is your operation. Okay, that represents your operation, no. If this is your if this is your first operand, okay, your second operand is actually is a sum, okay, of two operands pa. So say B and C. Okay. Now, if this operation, okay, possesses the property of distribution over addition, okay, it means that you can apply that operation to individual terms of the second operand. Okay? So which means equivalently, this operation can be, or this expression can be rewritten as A operation B, okay, plus, okay, A operation C. Okay? So ayun, you would observe that the multiplication operation is distributive over addition. Okay? Simply because alam natin na if you have the expression A multiplied to B plus C, ito ulitin ko lang halos to, you would have AB plus AC. Okay? So, but can we actually say that the addition is actually distributive over multiplication? So, pag ganun yung statement natin, that means that this is the operation, okay? Ito yung isang operand. The other operand is actually is a product operation. So BC. Okay? So obviously, hindi rin ma-apply yung distribution dito or yung distributive property. So that means that addition is not distributive over multiplication. Okay, so we may not we may really be not, or we may be ignoring this fundamental facts about your or fundamental properties of your operations. Pero may mga properties of your of your operations that if you really understand, okay, by heart, um mas lalo yung ma-appreciate yung yung arithmetic at saka yung mathematics. Okay? So, ayun. And sometimes knowing too much naman of this would lead to some confusion kapag naman kinonsider nyo yung operations that are operating on, say, a different number system. Okay? Ano yung ibig sabihin? Um, kung mare-recall nyo, ito, medyo additional info lang. Kung mare-recall nyo at kung nakapag-aral na kayo ng tinatawag na Boolean algebra. Boolean algebra is establishes rules for operations of so establishes rules for operations that assumes, okay, that assumes that your operands would take only two values. Okay? So establishes rules for operations of operands that take on two values only. So yung operands nyo may either be simply 0 or 1. Okay? So yung Boolean algebra, okay, are the rules for those for those situation. Okay? So iba yung algebra that we use when we assume that our operands would be decimal numbers. At iba rin yung algebra na ginagamit natin, or iba rin yung rules of the algebra that we use if the operands, okay, of those operations that we will use can only take on two values. Okay? So ang point ko is pag-aaralan nito sa sa logic circuits. Okay? Kung makukuha niyo na siya. And if you have discrete math, you would also have been able to study Boolean algebra. Okay? So, yan, sa mga courses na yan, those are the courses that you would study Boolean algebra. Okay? My point is kasi, in Boolean algebra, this is actually a valid operation. Okay? So, an operation such as A or addition there's no addition in Boolean algebra. Plus here represents the operation OR, while this represents the operation AND. So there is a rule under Boolean algebra that A or B and C, okay, equals A or C and B A or B. So i-distribute natin ito over the OR operation. So ganun yung may ganung rule sa Boolean algebra. Okay, while merong pero sa algebra sa algebra that we use for decimal numbers, okay, addition operation is not distributive over multiplication. Okay? So, yun. So these are the beauty of your math. Okay. Now, having said that, okay, since the convolution sum or the convolution sum operation is distributive over addition, okay, so ibig sabihin pwede natin i-distribute or pwede natin i-apply si distribution operation, or pwede natin i-distribute yung operation over the sum of terms, okay, or the sum of two operands, okay. That would mean that the convolution of x and the sum of h1 and h2, okay, is equivalent to the convolution of x and h1 plus, okay, the convolution sum of x and h2. So which means by applying the distribution, or by applying distribution over addition property of the convolution sum, okay, itong dalawang expressions na to are equivalent expressions. Okay? So what does it imply din sa physical systems natin? Okay? Recall that sequences, okay, that are added, okay, sequences that are added can be operated in this manner, okay, or can be represented visually, or can be represented visually or through the block diagram in this manner. So meron kang signal, say x1, okay, that is your signal x1. Tapos papasok yan sa isang signal adder, okay, and then another signal x2, okay, also goes into the signal adder, okay, and then the adder sums up the two signals, or the two sequences, producing the sequence x1 plus x2. Okay, now instead of merely signals as inputs to your signal adder, pwede nating gawin is that the inputs to the signal adder may instead be kaya lang ire-red ko siya. So yung inputs dun sa ating signal adder may instead be an output sequences from two different sequences. I mean two different systems. Okay? Which is fed by a common input. So again, instead na yung input, kasi kanina ang ginawa natin is that yung signal adder nyo, ang inputs niya signals lang. So I produce now another signal as an output. Okay? This time, instead of having simply signals, okay, to be fed as an input to your signal adder, we instead have these signals to be outputs, okay, of LTI systems, okay, that are produced, okay, or that produce those outputs, okay, because they are fed with a common input sequence. So say let the common input sequence be x of n, okay, and then the output here, okay, the output of your signal adder be y of n. Now these two systems, or let these systems be represented by impulse responses h1n and h2n. Okay? Now, kapag inanalyze natin tong system na to, okay, by analyzing the signals that goes around this system, okay, we will see na the system represented by h1, okay, produces the output x convolved with h1, okay, as an output to the system, while the system represented by h2, okay, produces the output x convolved with h2 as an output. Now itong dalawang signals na to, okay, are to be added, okay, which produces the output sequence. So therefore, your output sequence is actually x of n, or the convolution sum of x of n and h1n, okay, plus the convolution sum of x of n and h2 of n. So yun yung output sequence natin. Okay? we see, okay, we see that itong right side expression natin, okay, is actually the result or the expression that resulted when we applied the distribution property of the convolution sum over addition. Okay? So, ibig sabihin, itong expression na to, equivalently can be written as x of n, or the convolution sum of x of n, and the sum of h1 of n plus h2 of n. So, again, nakita natin kanina, no? Nung in-apply natin yung distribution property over addition ng convolution sum operation sa expression na to, we were able to get this as an equivalent expression. Okay. Now, given that we have an interconnected system in this configuration, okay, in this configuration, and upon analysis, okay, we determine that the output sequence, okay, is computed using this expression, okay, then we can actually work backwards, okay. We can actually take back or sa addition kasi tsaka sa multiplication dito sa distribution of multiplication over addition, okay, parang yung reverse operation nito, okay, is actually factoring out your common factor for both terms. Itong a ninyo, ipa-factor out natin, okay, leaving the sum b plus c as one of the factors. So, dito, parang ganun yung nangyari. Okay? While we cannot say, or while we cannot use the term factor for your x, okay, or common factor, okay, for your x, okay, dahil hindi naman to multiplication, okay, factors apply to multiplication operation, terms apply to addition, okay, so wala tayong eksaktong name para sa x of n natin, no? Sa operand x of n natin. Okay, we'll simply call it as the operand x of n. Now we see that in both terms, itong term na to, okay, at saka itong term na to, both of them contain the operand x of m and convolve with two different sequences. Okay? So, in that case, kung babalik rin natin yung distribution over addition, okay, we can actually have the operand x of n, okay, to be operated in common, okay, with the operation, okay, that is left for h1 and h2. And that operation is actually addition. So, ibig sabihin, yun nga, kung i-reverse natin o babalik rin natin yung distribution over addition property kanina, makukuha natin ito. Okay? So, ano ngayon ng point natin? If we take a look at this expression, okay, at this expression now, okay, it seems that your y of n, okay, can be computed, okay, again, kung igagawin natin itong equivalent system, okay, or kung if we have to write this as an equivalent system, okay, we will have to preserve the output signal y of n or output sequence y of n and the input signal x of n. So this is now the reduced equivalent system of this original system. Okay, and we see na yung reduced equivalent system na yun, okay, is ito, yung h1 of n plus h2 of n. Okay? So, ito yung interconnected system. By the way, we call this interconnection as parallel connection. So, we call this, this interconnection, this configuration of interconnected system as a parallel connection. So, this is cascade. Okay, this is cascade, while this is parallel. Okay, and systems that are connected in parallel. Okay? Take note ang mga systems that are connected in parallel utilizes a signal adder. Okay? And when you reduce that interconnected system into an equivalent system, nawawala na yung signal adder. Okay? So that signal adder actually gets to be implemented inside the equivalent system. Kasi ang gagawin natin is yung addition instead of implementing it as a separate operation outside the two systems. Okay? We will instead operate on the sum of the two systems first. Okay? And have the sum of sequences, okay, as now the equivalent system to operate on the input fed so that we will be able to compute the output sequence. So therefore, ang ma-reduce natin once na itong parallel configuration na to is this system, this two signals at saka itong signal adder. So all of those would disappear once we reduce this interconnected system into this equivalent system. Okay? So ayun. Idagdag lang natin yung point na yun here. Kasi dito, pinoint out natin that, wait lang. So here, we pointed out that the associative property of convolution sum allows the reduction of multiple cascaded systems into a single equivalent system, while the commutative property of convolution sum allows for rearrangement of systems connected in cascade. Okay. So the last point that we would like to add here is this. The distributive property of the convolution sum operation, okay, over the sum of two sequences, okay, allows the reduction of again, multiple. Okay, we'll use the term multiple kasi kahit ilang parallel systems yan, it may be reduced into a single equivalent system as long as parallel silang lahat. Okay, so multiple, we call it parallel systems, okay, into an equivalent into a single, para consistent yung wording, into a single equivalent system. So ayun. So to conclude this discussion, we have discussed in this particular lesson, in lesson 3.1, one technique of analysis of your LTI systems. Okay. And that technique is the use of convolution sum. Okay. So that yung technique of analysis that we have discussed here in this lesson is the convolution sum. Okay. And this ito yung natin. Summary na to the convolution sum. Okay. And this technique could only apply to relaxed LTI systems. Okay, we can only apply this analysis technique, the convolution sum, as an analysis technique for relaxed LTI systems. Okay. And in this case, the LTI systems now, or LTI systems, okay, are or can now be represented represented by a sequence, okay, whose values, okay, are the values of the system, a sequence whose values are are computed whose values are computed by feeding the system with the input delta n, or the unit impulse input. So yung representation ng LTI systems natin is actually a sequence, okay, which is computed, okay, that sequence is computed by feeding the system with a unit impulse input, okay. And we call this sequence now, okay, we call this sequence now as your impulse, okay, response. So in short, impulse response represents, okay, your system. Or in particular, the impulse response represents your LTI system, relaxed LTI system. Okay, and we use the symbol h of n to represent the impulse response. Okay, now the representation of systems using this sequence instead of IOR makes it mathematically convenient now to compute y of n. Okay, so system representation using h of n, okay, makes it mathematically convenient to compute the system output sequence, okay, for an arbitrary input sequence. Okay, so and that manual computation is yun nga, gagamitin natin siya ng convolution sum operation. Okay, so also since the system representation is a sequence, or systems are represented by sequences, which is yun nga, yung impulse response. Okay, the convolution sum operation also allows for rewriting, okay, or allows for rewriting interconnected LTI systems into equivalent forms. Okay, so dahil nga since the representation of sequences, these sequences can be convolved, or they can be convolved. So therefore, if they can be convolved, it is possible that your systems, okay, or interconnected systems, okay, or systems that are connected in a certain configuration, okay, be reduced, okay, or be written in an equivalent form using the convolution sum operation and the properties of the operation. Okay? So, napakita natin yan kanina in the discussion that we had earlier. So, ang napag-usapan natin is we have systems that are parallel. Okay? We have systems that are cascaded. And we have systems connected as parallel. Okay? So, we were able to learn how to reduce and write equivalent systems, okay, that are interconnected in this manner. Okay, so that wraps up the lesson 3.1, okay, as a lesson on the convolution sum. Okay, now in the next lesson, okay, we will use, okay, the impulse response, since systems are represented as impulse responses, okay, or as sequences known as impulse responses, okay, we would be using these sequences, okay, to characterize your systems further. Okay, kung maalala nyo in previous in topic 2, in particular in lesson 2.4, okay, nabanggit yung properties of your LTI systems, which includes linear and nonlinear, okay, time invariant or time varying, okay, memoryless or static, static or dynamic systems, okay, and so on. Ang iba pang nabanggit doon is yung causal or non-causal systems, okay, and stable and unstable systems, okay. So in the previous lesson, we were able to characterize systems to be causal or to be stable using the IOR representation. Okay, this time, since we have an alternative representation for your systems that are to be considered LTI, okay, linear and time invariant, we will now express yung characterization na yun, okay, in terms of the impulse response sequence. Okay, so titingnan natin ngayon kung paano masasabing causal ang isang sequence gamit yung HN, paano siya masasabing stable, and also what are the other characteristics that we can read off from the impulse response of LTI systems. So that is for the next lesson.